I'm going to insert the dielectric. So I take a piece of glass and I'll just put it into that gap. Q3 cannot go anywhere because I have disconnected the power supply. So Q3, no change. If there is no change in the free charge, the ammeter will do nothing. So as I plunge in this dielectric, you will not see any reading on the ammeter. But as we discussed at length now, the electric field, which is the net electric field, will go down by that factor kappa. That's what the whole discussion was all about. That's going to be a factor of 5. And since the potential equals electric field times D, but I keep D at 7 millimeters, I'm not going to change it. If E goes down by a factor kappa, then clearly the potential will also go down by a factor kappa. So now you're going to see the second part, and that is I'm going, as it is now, I'm going to plunge in this glass, 7 millimeters thick. I put it in there. You expect to see no change on the ammeter, but you expect the voltage difference over the plates to go down by a factor of 5. So you will see that the propeller voltmeter will have a smaller deflection. You ready for this? There we go. Now you have a smaller potential difference, but there was no current flowing to the plates or from the plates. When I take it out again, the potential difference comes back to the 10,000 volts. So that's demonstration number 2. Now we go to number 3. But before we go to number 3, I want to ask myself the question, what actually happened with the capacitance when I bring the dielectric between those plates? Well, the capacitance is defined as the free charge divided by the potential difference over the plates. That's the definition of capacitance. And since in this experiment, as you have seen, the voltage went down by a factor of kappa, the capacitance goes up by a factor of kappa because Q3 was not changing. And so, since the capacitance, as we derived this last time for plain plate capacitors, I still remember it was the area times epsilon 0 divided by the separation D, since we now know that with the glass in place, that the capacitance is higher by a factor of kappa, this is now the amendment we have to make to calculate capacitance. We simply have to multiply now by the dielectric constant of the thin layer that separates the two conductors. This is the layer that has thickness D that is in between the two plates. In our case, I brought in glass. I could write down a few equations now that you can always hold on to in your life, and you can also use them in the 2 demonstrations that follow. And one is that E, which is always the net E, when I write E, it's always the net one, equals sigma free divided by epsilon 0 times kappa. There comes that kappa that we discussed today. Let's call that equation number 1. The second one is that the potential difference over the plates is always the electric field between the plates times D, because the integral of E dot dl over a certain pass is the potential difference. That's not going to change. And then the third one that may come in handy is the one that I have already there. C equals Q3 divided by the potential difference, which in terms of the plate area is A times epsilon 0 divided by D times kappa. Let's call this equation number 3. Now comes my third experiment. In the third demonstration, I am not going to disconnect my power supply. So now, number 3, I start out with 1500 volts, just like we did with number 1, but the power supply will stay in there throughout, never take it off. We start with D equals 1 millimeter, just like we did in experiment 1. No glass. I'm going to charge it up, just like I did with number 1. And of course, I will see that the ammeter will show this charge. See a surge of current. Now I'm going to increase D to 7 millimeters. Now something very different will happen from what we saw in the first experiment. The reason is that the potential difference is going to be fixed, because the power supply is not disconnected. The power supply stays in place. Look now at equation number 2. If that V cannot change, and if I increase D by a factor of 7, now the electric field must come down by a factor of 7. And so now the electric field will come down by that factor of 7, because I go from 1 millimeter to 7 millimeters. So now the electric field changes, because D goes up. In case you were interested in the capacitance will also go down by a factor of 7, because if you look at this equation, kappa is 1. If I make D go up by a factor of 7, C goes down by a factor of 7. Just look at this. Simple as that. So C must also go down by a factor of 7. Nothing to do with dielectric. Nothing. And so Q3 must now also go down by a factor of 7, because if the potential difference doesn't change, but if Q3 goes down by a factor of 7, if C goes down by a factor of 7, Q3 must go down by a factor of 7. This goes down by a factor of 7, this doesn't change. So the free charge goes down by a factor of 7. And what does that mean? That means charge will flow from the plates, away from the plates, and so my ammeter will tell me that charge is flowing from the plates, and so that hand there will go to the left. And so as I open up, depending upon how fast I can do that, charge will flow from the plates in the other direction. The charge will flow off the plates, and that current meter will show you every time that I open it a little bit, it will go to this direction. So let's do that first. No dielectric involved. Simply keeping the power supply connected. So I have to go back first to 1 millimeter, which is what I'm doing now. I have here this thin sheet to make sure that I don't short them out. It's about 1 millimeter. And I am going to now connect the 1500 volts and keep it on. And as I charge it, you will see the current meter